So now that you guys know how to use electronics desktop fairly well, actually, and of course, more specifically Maxwell, this is going to be very easy for you, I think. So we should be able to fly through this pretty quickly. The goal is literally to take one of these magnets that we've been playing around with in class and build up a good, appropriate Maxwell model of it. If you look through, if we want to call it a specification sheet, this is really the best that we can find for this. If you scroll through the description where we purchased these magnets, we'll find that we actually have dimensions that are provided. That 15 is actually for the diameter, not the radius. So these magnets are 15 millimeters in diameter by 3 millimeters thick. The other thing that's going to be important, as you'll see, we know the material is neodymium, but we don't really have any other information pertinent to what we're trying to do other than this. So write these down, keep them in mind as we move on to open up electronics desktop and start building up this model, because we're going to build one of these basically and probably duplicate it for the rest of the simulation models that we're going to build. When you open electronics desktop, make sure you grab the right version. I'm hovering over what I have anchored. Remember, it's 2023 R1, which is the current version that we're in. You'll find probably outdated versions on there as well. So please, to avoid any confusion, make sure you search this one down and go ahead and launch it. And we'll start building this model up. So I recommend probably the first thing you do is why not go ahead and save this project. Remember, projects have design types that are included in them. And our design type, of course, is going to be this Maxwell design type. So right now we have an empty project. I'm going to save it now. I'm just going to hit the save button. I want you to put this on your OneDrive so you can get access to it. And you can call it, I would recommend you call it something unique. I'm going to say Magnet Summative. And I'm going to put my initials on it, JPB. I would recommend you do the same. So let's save it. And we're going to go right to adding our Maxwell design. So remember, it's in the desktop tab over here, and I'm just going to choose Maxwell 3D. And our buttons and ribbons will change accordingly. And you'll see that I'm left here with this grid that looks like it's in the XY plane. Okay, so there's my origin. And let's start building up the magnet from here. The first thing I want you to recognize is that I have the ruler turned on here, so I can see what my units are. They're in millimeters. If for some reason your units are different, remember I'm on the Draw tab now, and if I click the Units button, then you can just change your units here. So before you do anything, I'd recommend you get to the same units. Let's go ahead and use millimeters. I think it makes sense in this example. That's how we measured it, or it's at least easy to convert to centimeters. The other thing is that my grid, of course, I believe your grid would be the same. It's in the XY plane, like I just mentioned. I don't think that that's going to be an issue for you, but if it is, remember, you can change the orientation of the grid right here. So if it looks like this, then you're in good shape. So the first thing I actually want to do before I start creating geometry using some of these buttons up here is, even though I have an origin and my coordinate system is shown here, I want to create a number of local coordinate systems through the course of this project. So we talk about this a lot. We talk about the global coordinate system. If the W is shown, that means that that's the working coordinate system. Anything that I do, or any geometry that I create, or I should say translations or rotations that will apply, will be applying with respect to this coordinate system. Very important, because you always have to keep in mind which one the working coordinate system is, and I'll do my best to remind you along the way. So the very first thing I want to do is, directly on top of this global coordinate system, we're going to create another one. And I'm going to look at these up here. The only option that I have right now is the very top one. That's called an offset origin. It's one of the easiest ones to actually create. I'm going to hit the button, and if you notice down in the bottom left, it's telling me to select the origin. All that I should have to do is just point to the origin. If I zoom in, you should see I'm right there at the center, and I'm going to click it one time, and now I get this new relative coordinate system. Some of these options here we might be covering later on, but you can always click on the new coordinate system and you can see what properties are associated with it to convince yourself that you have it as I'm describing here. And if not, remember, these are things that you can edit, so you can change the numbers in here as we'll be doing as we go through the session. In using the terms float magnet and anchor magnet in the context of the board game that we're creating in class, so let's just go ahead and stick to that convention, and I'm going to make it so that we ought to be able to, kind of keep track of these things by giving them common names. So instead of calling this relative CS, CS is standing for coordinate system, let's go ahead and call this float coordinate system. So we'll go ahead and say float CS. So let's get right to it with the name changed. So what I'm going to do is come up here to these draw icons, and the one that works perfectly for us is draw a cylinder. So I'm going to click this button, and again down here at the bottom left it's asking me to enter the center of the base of the cylinder. Well, that's going to be right in the middle of our coordinate system here. So I'm going to click once, and now it changes on the bottom left again. You can read it says enter the radius. So I'm going to zoom out, and I can use over here on the left hand side as a guide. I can try to get as close to 7.5 millimeters. I'm going to show you a little trick though. Instead of trying to get the number perfect the first time, it's really easy just to go ahead and let it drop anywhere in the space. I'm also going to do the same with the height. The next question is, or I should say instruction is to enter the height. I'm not going to worry about trying to get the exact height. I'm just going to do something close. And what I can do now is edit. So now with the basic object there, I can click on the create center icon here in my model tree, and when I do that, I can go change these values to exactly what I wanted. So if you remember the radius was given to us from the specification that I showed earlier, and it was 3 millimeters. I'm going to actually type the mm. You don't have to. Make sure that it shows up as the appropriate units though, so do everything you need to get those to work out. And of course the height, if you remember, I just realized the radius I gave it was not 3.5. I'm thinking of the thickness. I meant to say 7.5 because that's half of 15. So that's our radius, but the height for us would be the thickness, and that was 3 millimeters. So that's all you have to do to get the cylinder. So go ahead and pause the video until you get exactly what we're looking at here, and then we'll continue on. One thing that's very important is to make sure that this object that is called cylinder 1 is indeed associated with the appropriate coordinate system. It should be float CS1. In fact, now's a good time to rename this. With cylinder 1 highlighted, I can just come into the name property, and I can go ahead and call it float. And that uniquely identifies it. I also wanted you to verify that if I click this create cylinder icon below the new name float, it does indeed tell me that it's connected to this coordinate system which we created earlier, float CS. If that's not the case, now's the time to change that. In order to change that, of course, all you'd have to do is just choose it down here. Okay, so we're already in good shape, so we're ready to move forward. So now we're going to take the magnet and apply magnetic material to it. Right now you'll see from the modeler tree, it has a property of vacuum. So what I'm going to do is right click on the vacuum, I'll go to properties, and we'll give the material browser window a second to come up. And when it does, we can either scroll and find it, or we can search for it. And I know that we're looking for a neodymium property. So if you just type in the letters N, D, F, E, and then number 30, it should come up right here. If you're not seeing it, then go ahead and scroll down and find this. So you can write that down. I see it right here in our systems library. If I choose it here, it's going to select it for me. So search works. Before I hit OK, I want you to go to View and Edit Materials. We have to make a change before we use it. And when I do that, it brings up a panel that has much more information. You probably recognize some of these names and terms from some of your physics classes: permeability, conductivity, Young's modulus, Poisson ratio, things like that. We are interested in this thing called magnetic coercivity right now. And the first thing I want you to do, the only thing I want you to do right now, is change the unit vector for the direction. So this is a vector quantity. So this property called coercivity is a vector quantity. And you remember unit vectors from all of our discussion of vectors. This tells you the only direction defined right now for this material is in the x direction. I want that to be the z direction. And I'm going to change it to 0. And then for the z, I'm going to make it a 1. And remember, those are unit vectors. So they are dimensionless. They're just pointing in the direction of where this coercivity is taking place. So I'm not going to change the magnitude. We'll do that later. I'm going to just go ahead and say OK for now. And when we do that, you should notice that we have what looks like a copy of the material here, because this one is actually in our project and not our system library. With that, I'm going to go ahead and click OK. And you should see the material value has gone from vacuum to now this neodymium Fe30. Go ahead and pause the video if you need to get caught up, and then I'll continue on. Got a few more things to do before we're able to run a simulation of this. The first thing, or I guess the next thing, is going to be I want to apply something called a mesh operation. What I'm going to do first is actually click on the float object, and now with that selected, if I break down the project tree and I look for mesh, if I right click, I can now assign a mesh operation. And what I want to choose is inside the selection, and I want it to be length based. So pause the video for as long as it takes to get this dialog and choose length based. And when we do, we can leave the name the same. I'm going to go ahead and change the max element length to 1 instead of 3. Everything else will stay the same. Say OK. You can always come back and verify that your mesh operations have been applied to the right place by simply selecting on the length 1 object and now right-clicking and showing select assignment. So the fact that it highlighted it when I said select assignment tells me that it has been properly applied. So now with that done, the next thing that I'd like you to do is to add what we call a analysis setup. So if I right click on the analysis node, I'm going to go to add solution setup, and the only thing I want you to change here is this % error to 0.1, and that's going to be it for now. I'll just say OK. So you should see this plus sign comes up because now we have the setup, and of course the properties tells you what has been assigned to it. So we're getting pretty close. The last thing I want you to do is to create the surrounding air box. So right now, if I zoom out, you don't see any other objects. We're going to create what's called a region. And if you look up here on the Draw tab, you'll see this little red cube that says that has the Create Region nomenclature. When I click that box, I basically am being asked to fill out a form. I want to pad all directions similarly, and I'm gonna leave that toggle where it is, and I'm gonna choose absolute offset, and I'm gonna say 100 millimeters. Okay, so once you have that, go ahead and say OK, and everything just got highlighted because it instantly selects it. And you can see it's just this vacuum region that was just created. It knows that this is basically defining the region of things that I want to solve. So whenever we do a simulation like this, we always want to remember to add, to have all the components inside that we want to run simulation on inside of our region. We should be ready to get a solution out of this, so I'm going to move over to the simulation tab right here, and let's go ahead and hit the validation button and see if we forgot anything. If everything turns up green like this, then we should be in pretty good shape. So I'm going to go ahead and choose Analyze All, and before I hit the button, if you have your windows set up like this where Message Manager and Progress is available, you'll be able to see any maybe errors that pop up along the way and some progress that's taking place. If not, you can go ahead and hit either one of these icons to bring it up, or you can also go over to View and select the windows there. So since mine's all set and ready to go, I'm just going to hit Analyze, and we'll watch it run through this solution. You can pause if you still need to get set up. You'll notice that it's going through a few different stages of the simulation. There's this thing called the adaptive pass process we've spoken of a little bit, and it's gonna go through as many adaptive passes as needed. I'm gonna pause it while it's running the simulation, and then when it's complete, we'll talk about what that meant and the results. So for me, it was about a couple minutes, and you'll notice that my progress bar is no longer moving. I've got some text that's popped up under my message manager, and if I expand that out, you hope to see something like a normal completion. So it at least met the criteria that I gave it before we set that simulation up. I'm going to look at a couple things. I want to go to the results tab, and I'm going to look for this solution data first. When I bring up solution data, I've got a number of different tabs here. And the one that I want to focus on is I'm already on the conversions tab. And I'm going to look at the plot view, and I'm going to change the Y to delta energy. And what I wanted you to see is that there's a connection with the number that we actually set up in the simulation. So we had a target. If you remember in the analysis setup, we changed the 1% to 0.1%. That's the target error in the computation. So we basically said we wanted 0.1% of error. I'm not explaining that in a lot of detail right here, but it's important to know that whenever you run a simulation, you should get a plot that shows that as it goes through these adaptive passes, you ultimately get a reduced error. And what you want to end on is the number that is below the criteria that you set. We set a criteria of 0.1%. The last two passes were below 0.1%, and it's calling that accurate. That's what we mean. We defined what accuracy means in terms of percentage energy error, and that's exactly what this is. So this is a successful result. With that, I'm going to close this out. And the last thing I would like to do is plot the magnetic fields just to see if it's consistent with what we expected. So we've done this probably before in class. What I'd like you to do, if you don't remember, is open up the planes icon here, and let's go ahead and choose. We may as well choose 3 planes. Right now, float and global are, if you remember, they're at the exact same location, so it doesn't matter which one we choose. I'll go ahead and choose float. That way the planes are going to be connected to wherever that magnet moves. So these are artificial. These are like infinite planes. It just gives me some structure to be able to view the fields on. So these have to be selected. So make sure you've actually highlighted them. You should see them visible there. Keep it that way. When you go over to the left-hand side, you want to look in the project manager for field overlays. Right-click on field overlays, go to field, and we're going to choose B, and we're going to choose, let's start with the B vector and see what this does for us. We have one more. We'll just go ahead and use the defaults here. We're not going to change anything. Click through that, say done, and we should see magnetic fields, and hopefully this is consistent with what you were expecting. If you remember, magnetic fields always have a north and a south pole. We played around with these magnets on the table to make decisions about which ones were aligned and which ones were not aligned. So choosing the north or south pole just by placing them next to each other, if they attract or if they repel, you know that the poles are aligned. You'll notice that the z direction is where these vectors are basically pointing up, going through the negative z to the positive z direction, and that has a big part. That actually has a completely in part to do with the fact that we changed that unit vector in the material setup. So by doing this, we're basically telling the material the magnetization direction. For things that take place after that, the magnetic field is behaving in the normal way outside of the region of the magnet. So if you place objects that are magnetic in the vicinity, they should see the effect of these magnetic field forces as you're seeing them here. You'll notice that the fields, the vectors that are plotted in the x-plane, they are all pointed down in that direction. In the YZ plane, you'll see there's a certain symmetry, right? So it's hard to tell which plane you're looking at if you go through 90-degree angles of these, and that actually makes sense with the symmetry of this magnet. So far these magnetic fields appear to be at least qualitatively good, and the next step is going to be to see if we can match this to what we actually measured in the classroom. So to conclude this first task, what I'd like you to do is let's go ahead and rename the design, not the project. We've already named the project, but I'd like you to keep track of these individual designs. And I'm going to right click and rename, and let's just say, let's just call this Task 1. And if you go back to our PowerPoint presentation when we started off, everything that we wanted to accomplish in Task 1 with that very small bullet list was accomplished in this simulation module. With that done, make sure you save your project. Again, it should already be on your OneDrive. Subsequent lessons are going to have us probably duplicate, copy this Task 1, and make multiple design types. So that's it for this session.